ladies and gentlemen. Our program will now begin. Please welcome the CEO of Churchill Club, Karen Tucker.
Hello, everyone. Thank you so much. Thank you very much for coming out and joining us tonight. It's great to see everybody. My name is Karen Tucker. I'm Churchill Club's CEO. And tonight we explore quantum computing technology, the state of its development today, possible role in innovation, economic growth, and the times ahead, where it might have the greatest impact, et cetera. And with us to weigh in are Arvind Krishna from IBM, Cam Moeller from the Applied Physics Department at Stanford University, Bob Stolte from Jpmorgan Corporate and Investment Bank. Welcome to our speakers. Thank you very much for being here. And here to moderate the discussion is Martin Giles from MIT Technology Review, who was of huge assistance also in framing the content for this program. So thanks and welcome, Martin. Finally, we thank IBM for making this discussion possible, especially Arvind Krishna, Vinita Durrani, and Angela Sullivan, and for bringing in the IBM Q and the cloud demos for the audience to better understand our topic tonight. So thank you very much for that. A few words about Churchill Club. Since 1985, actually, the year of Windows 1.0, we have been convening conversations around the incredible changes that have been occurring, technology-driven changes on business, society, et cetera. And we are very opportunity-focused. We think in terms of if there's a trend that we agree has important consequences, what might it represent for opportunities ahead, for innovation, for economic growth, and for societal benefit. We always ask our speakers not to pitch or promote, but rather to come with the spirit of advancing collective knowledge. If you're not already following us, we invite you to do so. You can visit us on Facebook, LinkedIn, and by the way, the Twitter code for tonight is simply Churchill Club. So let's now get the conversation started and welcome our speakers and Martin to the stage. Thank you.
Okay, thank you very much, Karen, for that wonderful introduction, and welcome to what's going to be a fascinating evening of conversation. As Karen mentioned, I'm the San Francisco Bureau Chief of MIT Technology Review, and as part of my mission, I try to look what's coming beyond Moore's Law, beyond the end of this wonderful kind of multi-decade richness that we've been gifted by the doubling every couple of years of the number of transistors that can fit on a microchip. And you may know that there's also a Moore's law, which is that every 2 years the number of people predicting the end of Moore's law doubles. And so I'm very, very grateful to be able to contribute to that Moore's law. But it really does look like we're coming to the end of an era. According to some estimates, by 2020, 2021, we're going to get to like sort of 5 nanometer chips, and that's really the kind of end of this kind of Moore's law trajectory that we've been on. So what comes next? And I look across the fields. One which I look at very closely is quantum computing, and so I'm delighted to have the panel here with me tonight. And I'd just like to take a brief show of hands, if you wouldn't mind. I mean, how many of you would class yourselves, and let's do 3. First, how many of you would class yourselves as really deep quantum experts? Okay, that's good. That's good gauge. Number 2, how many of you would say that intermediate, kind of like me? Okay, and how many of you say relatively neophyte? And so, okay, that's good to know. So we can just gauge how we go in. So I would like just to very briefly give you a little outline of the way I'm going to handle the conversations, and then I'm going to ask my panelists to introduce themselves. And what I'd like to do, we're going to split this into kind of 2 halves. So the first half, we're going to like deep dive into the technology, and we'll do it in a way as best we can to make it sort of as accessible as possible, but also to sort of hit all of the kind of key technical points that really are important to know. And then in the second, and I'll break at the end of that part for Q&A from the floor. So anything you want to ask around that first portion of the conversation, ask then. And then we're going to look at the application of these technologies in various different business areas and kind of lessons that you as very smart operating executives or people who are in the technology industry need to be thinking about in terms of how these technologies may actually roll out and be applied. There's a lot to cover. You'll hear things like superposition and entanglement, and don't panic. We will do our best to sort of spell out what those are. Okay, without further ado, I'm going to ask my panelists to introduce themselves. Arvind, would you like to go first?
So, Arvind Krishna, I'm with IBM, and I get the privilege of leading our global research team. And one of the topics that we are talking about is quantum computing.
And this is your computer here, right?
This
Very
is our
nice.
computer.
Is there a laptop version?
Maybe in 100 years.
Maybe 100 years. Okay, that's one good gauge.
But you can access it from your laptop.
You
now,
can
so-
access it, that's true,
Yes.
through the cloud. Absolutely right. Cam.
So I'm Cam Moeller, and I'm a professor of applied physics and physics at Stanford, where I do research on experimental low-temperature physics. In my research group, we study quantum materials and devices, and we have some instruments that look very much like that one. I'm also the Senior Associate Dean for Natural Sciences and the co-chair of Stanford's Long-Range Planning Group for research. And in that context, we've been looking at quantum more as well.
Fabulous. Bob.
Great. I'm Bob Stolte, and I'm the New York banker in the stage.
Got the suit.
I'm one of the, exactly, this is business casual in New
Took
York.
the tie off just before.
I'm one of the chief technology officers in our corporate and investment bank for Jpmorgan, and I've been working in the field of basically what I think of as applying technology to solve financial services challenges and advancing the industry for about 22 years, and have been focusing on quantum and other high-performance computing advances in addition to what I would say is my day job for about 2 years now.
Wow. Perfect. Thank you very much. So a great sort of complementary set of skills and backgrounds here. I mean, let's start by sort of just diving into the kind of physics behind all this. I mean, Cam, without sort of requiring you to give a lecture, sort of the key points of what's brought us to this or the point of this revolution today.
Absolutely. And some of you who I know in the audience, I saw you raise your hands about being neophytes, and I know that you're a little bit downplaying your expertise there.
Oh, there's some
Yeah.
quantum cheats. Okay.
Okay, so, so basically in the quantum world, there are a couple things that happen that don't happen in our everyday classical world. One of them is that there can be a superposition. A lot of you, how many people have heard of Schrödinger's cat? Okay, so Schrödinger's cat is the cat that is both alive and dead at the same time, and is a thought experiment to illustrate how ridiculous quantum mechanics is, because a cat can't be simultaneously alive and dead. But in quantum mechanics, objects can be. That's called superposition. In addition, there's a property called entanglement, which is that different parts of a system, different subpieces of a system, can also have a superposition of different states. So in this case, you could imagine a pair of cats in which one cat is alive and one cat is dead, but simultaneously each member of the pair could be each. And that's kind of like entanglement. So if you imagine a bunch of bits that can all occupy multiple states at the same time, you can see that you can get a tremendous speed up in the parallelness of computation. And that's the basic overview of how quantum computation works.
Got it. And if there's anyone from the if there's anyone from the ASPCA in here, we love cats really. But I mean, I think this sort of key is the qubit, right? I mean, so there's in classical computing there are these ones and zeros, whereas in quantum it is these wonderful sort of core things that make this possible is called qubits. So they can be at 1 and 0. They can be real cat, dead cat, live cat at the same time. Right. And so this whole coming together has allowed a company like IBM to produce a machine like this. Arvind, how are we positioned today, do you think, in terms of advancement in the field? Are we kind of like at the ENIAC stage of computing, classical computing way back when, or are we a little bit beyond that?
Oh, I think we are quite a way beyond that. ENIAC, I think, if I remember, was 1945, and I would say that the first commercial set of computers, if I go back forward, was 1964. That was 19 years. So I think we are quite a bit beyond that. I think we are somewhere between, is it a year or is it 5 years? But that's the window in which I would put we are going to get significant commercial uses of quantum computers.
Within 5 years?
Within 5 years. So that's the prediction Algo put out there. And then if you back up from there into, okay, how long does it take us to get ready for learning how to use them? Because it's a different kind of mathematics you need to do. A lot of the classical programming you've done is not going to apply, but people with certain skills are going to be able to use it, and that's the training you need to do. I think we also are going to have to make a lot of advancements on algorithms that are applicable to these machines, and there is work going on there. So you put all that together, and then to go back to what Cam said about this superposition and entanglement, and then you're going to hear some other terms. We'll put just one more maybe, which is called coherence time, which is, think of it more simply. How long can you use the machine for before it kind of goes off into its randomness? And we put those three together to then say, okay, how do I write an algorithm that takes advantage of the machine using those properties to make some things? And I'm saying within 5 years, you'll see someone do something that's going to make everybody stand up and say, wow, how's that possible?
Bob, you're nodding. Agree with that?
Yes, I think it explains why industries like financial services are suddenly interested. I think it is about learning almost a new language, not a programming language, but in general, as you think about how in a world where in 3 to 5 years, I won't give you one. I think that what we want to do and what a lot of industries are doing now is starting to educate themselves, starting to show up at the party to be prepared for that eventuality. And I do think it's an eventuality at this point.
Right. And I think it's important to sort of just be clear that this doesn't mean classical computers are out of the window by any shape, sense, or form, right? So most of the compute that a quantum computer does is kind of taking out specialized areas.
Look, classical computers are going to be here forever. Let's make one statement clear.
That means half of Silicon Valley is breathing a sigh of relief.
I mean, like Bob's in banking, but if you have a retail bank account, you need to know with determination how much money you have. That's going to be on a classical computer forever. A quantum computer may give you a different answer each time. Some may like it, but most don't. Right? But for some other problems that are probabilistic in nature, a quantum computer is kind of fit for purpose for those. And so you should think of them as being complementary, not as replacements, which I know some people do.
So IBM Financial Services has got to be watch out for that one. That's quantum. Yeah, sorry, Cam.
I would just add that a lot of the really exciting research is on the integration of classical with quantum, both the integration of classical hardware with quantum hardware, and also figuring out in terms of algorithms. We have quantum algorithms and classical algorithms, and how can we put them together and make hybrid algorithms? So the quantum computer is really doing what it needs to do.
Got it. And that's a very different skill to sort of classical programming. So, a programmer who's worked on any kind of sort of classical computer, can they easily sort of flip over to programming for a quantum one?
Well, it depends on what you mean by programming. I mean,
Okay.
I think one of the really exciting things that's coming along now, and we'll probably hear a little bit more about it, is the fact that there are getting to be sandboxes where people can start playing with these things. And I think that's going to really impact the educational environment. And it'll also make it easier for people who are experts to flip over and just try things out a little bit.
Look, I think there's a couple of levels here. So there are some people who need to understand, let's call it quantum mechanics, linear algebra, or the mathematics, and that's going to be a small set of people. Like has happened in every computing paradigm, they'll learn to abstract some of this away, and then others can use those, and that is then opens up the aperture to a lot more people, I think, right? Now they'll still need to know some, because I think in this world it's going to be hard to abstract the hardware away completely, but they don't need to understand as much as the quantum physicists, right? So there's a small set, let's call it the inner circle, which opens it up for a much bigger set of people outside.
Got it. Let's talk a little bit about the hardware here, because these are very sophisticated machines. I mean, you see the size of that one there, and that normally lives in a case that takes us to sort of deep space temperatures, right? I mean, so what kind of model is that, and how does that work?
You mean, how does it work that it takes us
so
to low temperature?
What's the form, the superconducting model? What exactly is that
Okay,
as a quantum computer?
So the qubit is basically just a Schrodinger cat. You just need something that can both have a superposition and be entangled. And then there's the question of what do you make those qubits out of? So 20 years ago, there were lots and lots of things that physicists were considering making qubits out of because many things can be quantum. And I think a lot of the research now is on trapped ions, which live in very large vacuum chambers, and on superconducting circuits, which, as you say, tend to live at very low temperatures.
So those are the two. So there's trapped ions, and then there's superconducting circuits.
I think those are the two main paradigms. And then there's a lot of classes within both of those.
Got it.
And so this is an example of the kind of equipment that you need if you're going to use superconducting circuits.
Got it.
Because they need to be cold to operate.
And
I just got to tell the room an interesting tidbit, because Martin said it's as cold as outer space. Outer space is like boiling. It's like melting iron compared to the temperature these things work at, just so that you all know.
ground control to Major Arvin.
So it's, did I think correctly? Outer space is 100 times hotter than the inside of these things, just to be clear.
So outer space is like a few Kelvin, for those of you who know the different temperature scales, and these things are a few millikelvin.
Is that near deep space?
When that's operating, it's as cold compared to outer space as, say, outer space is compared to the temperature of the sun.
And why does it have? Wow. Why does it have to be like that? What's the reason for that?
You basically need to suck all the thermal energy out of the materials and devices so that you have less noise. First of all, so that they can be superconducting in the first place, but second of all, so that the superconductors themselves, once you have a superconducting device, cannot have the noise that it would have if it were in an environment where temperature was giving it thermal fluctuations. Thermal fluctuations is just when something's at a certain temperature, there's a lot of energy kicking around in its molecules.
Got it. And noise, just so we get to the technical term, there's a sort of, Arvin talked about coherence. So you need to keep these qubits in this kind of superposition state so that they can be 1 and 0 at the same time, and entanglement. And any kind of disruption to that state would lead to fast decoherence.
Right, absolutely.
So you need to keep them as isolated as possible.
So you need to get them cold so they can even start working, but then once you're there, you need to do all kinds of other work to isolate them from environmental influences as well.
Got it.
You should think about it this way. Energy is noise for this thing. And temperature is energy, right? This is a simple way. So you got to get rid of the energy, which means you got to get rid of the temperature. And 0 would be ideal, but you can't be 0 because 0 means life stops. I mean, sorry, at the subatomic level, life stops. That's not good. So just above that.
Yeah, you've got to get rid of the random energy. You want only whatever energy you put in it because you're controlling its information.
That sounds like really complicated. What about ion traps? Are they just so much easier to do, or they have their own kind of levels of complexity?
Well, ion traps generally, to have an ion trap, you generally need to have it so an ion is an atom with some of its electrons stripped away from it, and those are useful because you can use electric and magnetic fields to trap them and hold them in position. But they usually need to live in a vacuum chamber. If I tried to make an ion trap in this room, the molecules of air would not let that be possible. So they need to live in a vacuum chamber, which is usually a pretty big apparatus. And then you can't trap, there's a question of how many superconducting qubits can you build, how many ions can you put in an ion trap. They have similar levels of complexity, I would say.
Okay, in different ways, right.
In different ways.
Bob, have you experimented with different kinds of quantum computers, or have you
we haven't actually done anything with ion traps. So
okay.
We've been strictly on the superconducting side.
So you've been in outer space, deep space, for a while.
The ions in the ion trap are also very cold.
Okay.
Yeah.
I mean, there are. How cold are they? It's like my refrigerator cold. Or
well, they can be actually even colder than what sits in there, but there's fewer atoms. So it's easier to suck all the energy out of one atom than it is to suck the energy out of something that's built out of a lot of atoms.
Right, got it.
Yeah.
In the spirit of sort of fair play, I mean, there are some other kinds of approaches. So there's one, wants to use silicon, plain old, good old silicon, to make a quantum computer. Another one says, actually, what we really need is something really special. Let's call it topological, and we'll call it the marjoram fermion. I think I pronounced that correctly. So thank you for the... I'll come and sit there, and you can come and do my job tomorrow. That'd be great. You write my article on deadline. Wonderful. So there are these other approaches. Why are these two the ones that have kind of got most traction so far?
Well, I'll give my answer and you can jump in. So Majorana fermions are actually, we shouldn't necessarily call them fermions, but never mind. Majorana particles are Majorana particles are one of the types of superconducting qubits, actually.
Okay.
It's a type of superconducting qubit that hypothetically could be much less susceptible to environmental influences that cause it to have errors.
Got it.
And it's a type that we're studying in my lab. So they're a subcategory of superconducting circuits. Now, why superconducting circuits? Well, you really want something that works. And you also, if you can, you want something that's solid state. And for those two reasons, I think superconductors have really emerged as a pretty good bet.
Got it.
So for those of us who like to build stuff which actually works, I kind of come to a simple answer. So the two that we talked about, the current superconducting circuits and the trapped ions, we actually know how to build them. Some of the others have been posited, but people don't quite know how to build them, certainly at scale. So there's that little matter of importance. And then there is the other matter, we talked about superposition, entanglement, but we forgot to say, and we need to control those. They shouldn't superimpose or get entangled at random or by themselves. We need to be able to program it or control it, and we can only do it to these two kinds. So the others can exist on paper, but we don't quite know how to do any of the other things to them.
Got it. And how long are we able to keep qubits coherent for at the moment? I mean, what's the kind of time frame we're looking at?
Right now we are at about 100 microseconds. We believe we'll get into the milliseconds in the next few years. I think beyond that, we don't know.
Wow, that's not very long. Okay, but I guess, so this is why it's so challenging. So I mean, just let's briefly sort of step back and recap, and then we'll go forward. So we have these unique qubits, which can be 1 and 0 at the same time. Therefore, if you add another qubit, it's sort of exponential processing power that can come from that. They are entangled, which even Einstein...
I got to get back to your Moore's law.
Yeah.
You said in Moore's law, I think it doubles every 18 to 24 months.
Correct.
Here, if you add 1 qubit to your machine, it doubles in power.
Got it.
So there is an equivalent there. So when you went from 5 to 15, or actually 5 to 17 qubits, you didn't get 2x, you got 4,000x.
Right.
In terms of power of the machine.
But it's kind of like a super Moore's, right? I mean, because it goes way up. From the moment you hit 100 qubits, you're like...
100 qubits here beyond what anything can do it. Somewhere around 60 qubits, if they were all perfect, which they're not, you would be beyond the power of any supercomputer that is currently known. Somewhere around there.
Got
But
it.
it might be a good time to distinguish between logical qubits and physical qubits.
Oh, yeah.
Oh, sorry to bring this. I was trying to kind of segue there. Let's distinguish. Karen, off you go. Off you go. This is really important. This is key, actually.
I mean, so there are these errors. So the qubits accumulate these errors. So a typical error rate is maybe something like 0.1% in the really amazing work that our friends in industry have done. Now, if you imagine that you have a spreadsheet and you're trying to do a calculation on your spreadsheet, and every time you access a number or use it in a calculation, 0.1% of those numbers change to some other number, that would make the spreadsheet very difficult to use. And so there's been a lot of work on algorithms for quantum error correction. And so you need a lot of qubits around in order to do the quantum error correction to give you a fully functioning qubit.
Right, so you got two approaches then. So that's, you make a logical qubit, which is much more correct or perfect out of physical qubits. Or the other thing which you can also do is say, I accept there's an error down at the bottom, and I now work with the physical qubits, but acknowledging they might have error. And now you got to ask yourself which algorithms are going to be reasonably robust in the presence of those errors, right? And that's an exciting question, because if you want to get all the way to logical, some competitions show maybe you need to make the machine 1,000 times bigger. Best case, maybe 100 times bigger. That's a lot bigger.
Just to get one logical qubit.
So there's a lot of I think both interesting applications and then science behind that to sort of bridge this divide.
And just in your 5-year time frame, Arvind, do we think that by the end of that 5 years we'll have cracked this problem, or will we still be struggling with trying to get a logical qubit?
I wouldn't say struggling. I don't think we'll have cracked this problem of that a logical equals a perfect physical qubit. I don't think we'll have cracked that in 5 years.
Okay.
However, I believe there will be enough applications or algorithms of great impact to a lot of industries that can use these imperfect qubits and still produce a huge amount of value. That would be my prediction.
Got it. So to very briefly recap, there's this amazing new way of computing. It does all these kinds of amazing things through things that we don't really understand, like entanglement and superposition, and it doesn't really work very well yet, but we have ways of fixing it. And in 5 years' time, this is actually going to be very powerful. And I think that this is the point. I sort of exactly, because when I'm writing about this stuff, it's really hard because it doesn't really, I don't get it. And actually Einstein didn't get entanglement either, so like don't feel bad about it. But the point is we have made major strides forward. And this point about error correction is critical because we need to be sure if I'm in banking, I don't want to have that 0.1. I think that might be a real problem for Jpmorgan on some kind of trades. Maybe not on all of them.
Well, I think there's to Arvind's point on what kind of math you're doing, right? A huge amount of what we do, and we'll come back to this on the application side, is really probabilistic computing, and you can brute force your way through some of those error situations, but not necessarily better than you can with a classical computer right now, but you can learn.
Got it.
Which is really kind of where we're focused right now.
So we are, I mean, Arvin sort of like 5 years' time, really useful stuff, but maybe this year, we get to the point that some people have called quantum supremacy. And this is, according to the definition, the point at which a quantum computer can perform a task that would be beyond the reach of even the most powerful supercomputer, or at least within anyone's reasonable time frame. What does that mean? Is it really significant? You're shaking your head. Okay, I think I know what your thoughts are. No, but tell us why you're shaking your head.
Look, I think the notion of supremacy I'm going to put aside, because supremacy says that a quantum computer is better than a classical computer at everything. And we just heard, even for certain banking things, you need a classical computer. So I'm going to put supremacy aside. Advantage may be a better word.
Quantum advantage.
Quantum advantage. So quantum advantage says I can solve a problem that would be uneconomical or infeasible to do on a classical computer. And so if you take that notion, is it this year or next year? Because this bar kind of moves a little bit. People claim that you cannot do a problem of a 50-qubit quantum computer on a normal computer. And actually, some of my colleagues actually demonstrated last year that that's actually not true. You can. Now, that bar then moved to 56. And so it's a bit of a moving bar.
Because the other side's moving too, right? Supercomputers are getting better, exascale computing's around the corner,
right.
Maybe.
So some of these things are going to be the notion of the algorithm, how noisy is it, can I do the error correction, how much of it, you put it all together. Quantum advantage says, though, fine, I could do it, but if that takes me a couple of $1 billion and this takes me a couple of million, I prefer this approach. I do think we're going to get there, I don't know about this year, but in the next short number of years.
That's very specific. Cam, you?
Well, I think once you reach this stage, whether you call it quantum supremacy or quantum advantage, where there's something that a quantum computer can do better than the best simulator that we can build with a classical computer, that's wonderful. It's a wonderful state to reach, whatever you call it. But what's next from that? How far do we have to go before the investments in developing algorithms for solving these interesting problems starts to pay off from there, right? And there's what comes next after that. Some people call it the quantum chasm, right?
The quantum chasm?
The quantum chasm, yeah.
Because there'll be a gap between...
Mm-hmm. Yeah, I think John Preskill called it the quantum chasm. I don't know if he was the first person to say it, but from the point where you get to the point where you have quantum computers with, say, 100 to 1,000 let's call them noisy qubits, right?
Right.
And to get from there to this dream of the universal quantum computer with millions of qubits that can solve many types of problems, there's a large gap across there. And I think chasm's not fair, but as we cross that landscape, we'll find more and more applications coming online and more algorithms being useful. It's not like nobody thinks that we get to 70 or 80 and then suddenly, wow, the full promise is realized.
Right, because we're at kind of 72 now, which is the Google one. Will we see 100 qubits within the next 18 months, Arvind?
Maybe.
Maybe. Okay. Okay, a bit more specific. No, okay. Okay, so we're entering, I mean, the quantum chasm is absolutely right. I think he also called it NISQ, N-I-S-Q, sort of noisy intermediate state quantum. So John Preskill is one of the kind of leaders in the field who's at Caltech, and he actually coined the term quantum supremacy, and then sort of like modified it a little bit. But this, this kind of idea of, yeah, we're going to have this noise issue with us for a while, and we need to address it in such a way that we can actually make these computers more useful.
Actually, I believe that these things on noise are going to be there with us for a long time. I don't think it's going to be, the intermediate stage is a long time.
It's a long intermediate.
It's a long intermediate. I fundamentally believe that problems that are underlying probabilistic in their nature, be it risk, be it simulation, and maybe quantum chemistry, are going to be robust with respect to the underlying noise if the noise is not too big. And sort of, and I think that that is where the science and the art is going to go.
I mean, I have seen some people say, actually, noise is just going to be too much of a problem. Quantum computers will never become really useful because of this noise issue.
This is like the people who didn't like machine looms?
And professor of computer science, University of Tel Aviv. Yeah, so, I mean, it's just, there is a debate still, I think. I mean, it's reasonable to say that some people would question whether noise will be, so your view very strongly is that this can, even now, we can address it through either the algorithmic approach or the additional qubit approach in ways that can still make these computers very useful.
That's a firmly held view. The fact that we can already solve, albeit very small problems, but real problems, tells you that it's possible.
Got it. We've covered a lot of ground there in a relatively short time, so I'm going to break for questions in a minute. So if you have questions on what we've just covered, please start thinking about them. I just want to ask one other question before I do that. We talked about quantum algorithms and the importance of getting software together with the hardware that makes this work. How many people are working in this field right now? I mean, are there like hundreds, thousands of people out there working on quantum algorithms, or is this still a kind of cottage trade?
I have no idea.
How many has Jpmorgan got? How many?
Less than 10.
Less than 10, and you're Jpmorgan. Wow.
Well,
Yeah.
the world has at least 80,000.
80,000 people working on quantum algorithms?
At least.
At least. That's how many of them are in academia and how many in industry? You think? Guess.
80-20?
80-20.
Where did you get that number? How do you define?
Yeah, I'm just trying to think 80,000. It's like,
I'd like to meet more of them.
Redefine the meaning of.
That's the exact number of distinct individuals who have tried to run a program on our quantum experience in the cloud.
Okay.
So at least 80,000 people have written a program that ran on a quantum computer. By the way, 4 million programs in total.
Okay. I think you got me there. All right, let's take some questions from the floor. Can I, there's just gentlemen at the front here, can I ask you, if you wouldn't mind just telling us who you are, or your affiliation when you ask your question, and try and keep it reasonably brief. Oh, sorry, we'll start over here, then I'll come to you. You have a very nice jacket, so we'll definitely come to you.
Hi, Kingshik Maitra with Microsoft HoloLens R&D, so do not ask me about topological quantum computer. I work on HoloLens, but I'll try my best to keep it non-technical, but I do not have at least the question I have in mind. I'm not able to frame it in a completely non-technical way because it would become incomprehensible.
Go for it.
So one thing I worry is, Arvind mentioned about scale, right? I do recognize the number of qubits you need to get to the level of complexity of an equivalent classical computer is much lesser than billions of transistors you would need on the classical side.
Yeah.
So one issue that comes to mind is, how do you test? If you think in terms of VLSI or chip testing these systems, the way I understand quantum computer is The time evolution doesn't happen through standard Schrodinger equation, but through unitary transformations. And when you measure through a Hermitian matrix.
So
if you
it's
take
test.
it and you destroy the system,
Right.
right? So in normal VLSI world, you are used to probing.
Yeah.
You are used to also some form of built-in self-test.
Got it. So what's
to
the second
so,
part?
So the question is, in the quantum world, how do you test the
Got it.
systems for scale?
Okay.
Are people thinking along those
Who
lines?
wants to take that?
I guess I will. So the answer is, because we already built 5, 16, 17, 20, 50, we have to test for those things.
Yeah.
So you test down at a chip level, you test whether single qubits are effective, those that pass it, then you work on making sure that the gate operations, what are you talking of, entanglement, etc., are accurate. And so the same way that you test classical computers, you can go test these. Now you're asking, I think, the implicit question, wait a moment, when you get 100 qubits all superimposed and entangled, how do you test for that? We are not at that stage yet, so I will not be able to answer that. But you'll have to chunk the problem down. And hopefully, I'm going to look at Cam and say, hopefully our theoretical colleagues will come up with some ways that you can still
So even 50
test it.
qubits are
We just
complicated
need to
enough, right?
Cam, do you want to answer? Then we need to.
I think as a general point of principle, you're saying you want to test something that can be either a 0 or a 1, but something that can be both at the same time. But I think in the modern world, we should all understand that algorithms that are probabilistic can be tested, right? There are many people who are probably everyone in your company who works on in general forecasting.
Quite a few regulators.
Is
actually.
probably pretty comfortable with testing probabilistic algorithms. So even though if a qubit does something, you can't say, well, it should be a 0, but you could say, well, 70% of the time it should be a 0, and that 70% of the time should be correlated with this other outcome over here. So you can very much study probabilities and correlations.
Got it. Perfect. Thank you for your question. We need to move on. Next question.
My name is Jim Handy. I'm an industry analyst following the semiconductor industry, and two things Dr. Moeller said really confused me. One of them is that you said that the materials that are used are solid state, and I thought when you got down next to 0 Kelvin, everything was a solid because all of the Brownian motion had been taken out of it. And then the other thing that you said was that it was very easy to take the excess energy out of a single atom, and I'm wondering how you achieved that.
Okay. Right. So probably I shouldn't have said easy, and I meant no disrespect to my colleagues in atomic physics. There are a lot of techniques for manipulating the energy of individual atoms involving light. So if you think of an atom, I'm answering your second question first. If you think of an atom, what kind of energy does it have? It can have the energy of its motion, so it can be moving. So you take the energy out of it by slowing it down, usually using lasers to transfer momentum to it, but you can use other methods as well. And then the other thing is, what state is the atom in? Is it in an excited state or not? And again, you use lasers to help the atom transition to its ground state. That's how you make atoms cold. It's not easy. It's very hard to make atoms cold. I mean, people have won a couple of Nobel Prizes for this in the last 20 years. I shouldn't have called it easy. And then your first question was about solid state. Yes, not everything is solid at these temperatures, but a lot of things are solid at these temperatures. But when you're building a computer, it's just really very handy to have circuits on chips, right? I'm not a technologist, but I'm pretty sure that circuits on chips are better than large vacuum chambers.
Yes.
It's just my intuition. Yeah.
Yes. I'm going to take the next question there. Yes, this gentleman.
Ian Thompson from the Register. Moore's law is basically just an engineering prediction at the end of the day. But when it comes to quantum, which is the tougher problem to solve? Getting the hardware right, or actually building software which works?
I think it's a bit of both, but getting the hardware right is probably more critical. Because if the hardware is not right, the software ain't going to help you. If the hardware is close enough, then actually the software can make the hardware look right. But the hardware's got to get close enough first. Not perfect, but close enough. But if the hardware is completely off, forget it. All the software in the world is useless.
Okay, we have time for 2 more questions.
Hi, it's Mike Shepard from Growth Point. Arvind, you alluded to maybe developments in physical chemistry or something that sort of insulates the quantum core, if you like. And secondly, is that going to be what makes it more available, you know, at higher temperatures or whatever it is? And secondly, you know, how do you deal with the potential error from the amplification or vice versa from the input-output systems down all the way to the core?
Okay, so part 1, I'm going to look at Cam to help me out. I don't think that we're going to raise the temperature in the intermediate term. So these things are going to be available as a service, but I think everybody's comfortable with cloud computing. So I'd say it's a cloud service, so you can do the cold temperatures in a given place. It doesn't need to come to your desktop or into every single data center in the world. So the installation that we are referring to on materials is more about how do you keep extending the range and decrease the errors. The decreasing of errors is going to come from the physicists who work on the underlying materials. I don't think that's going to come from other approaches. So that's what we reflect on there. And then the algorithms, I believe for the near term, will come from, okay, if I can lower the error rate, is it 0.1%, is it 0.05, something small, then can I live with what in the algorithm to go work with that?
Okay, and then one question over here.
Yes. Tom Faremsky, Silicon Valley Watch and ZDNet. What types of problems is this best suited for? Because it's going to do nothing for my word processor.
We're just going to segue to that.
But is it going to solve problems like protein folding? Where are we going to see the breakthroughs from this technology? And also, how are we're going to unlock the secrets of the past? Because now we can de-encrypt everything, right?
So I planted Tom to ask the question that would segue us to the next section. Great job, mate. Thank you so much. But they are really good questions, really good questions. So when is this actually going to get there? So I will take one more in lieu, if that's okay. Please, yes.
I'm Ann Matsura. I'm from Intel Labs, and I work on the quantum architecture and applications area. And I was wondering, for Arvind particularly, are you worried that the chip architecture itself will constrain the types of applications that you can run on the quantum computer? I'm saying that because we're working on small systems of qubits, running algorithms on very small systems of qubits with no error correction, and we're seeing that the connectivity makes a big difference on whether you can run the algorithm on that chip or not.
Okay.
I'm actually probably more concerned about inter-chip connection than single chip. Because you could sort of say in a single chip you can get to where you want to get to, but then when you begin to make bigger machines, so how many qubits are you going to put on a single chip? And now you've got to connect multiple chips. And now you're going to get all the gate operations, because what you're referring to is the gate operations between entangled qubits require all this stuff. I believe maybe on a single chip you can get all the way there, and now how about multi, and then how about if I go canister to canister, which is an unsolved problem.
5 years? Chip to chip?
Chip to chip we got to solve in the near term. Canister to canister, I don't know.
Okay.
Before we fully segue past foundations, I just want to get back to this question about the ions. I think there are a lot of very clever people working on ways to get all the advantages of an ion or an atomic state, plus all the value of a solid state device. So I just want to say there's a lot of work being done on that.
Okay, great.
Yeah.
Now we'll get Tom's question again. What can we do with this technology in the state it's at right now? So what's today, what can we do? And then when is it going to solve some of the problems that Tom mentioned around? Sorry?
Unlocking the past. We can de-encrypt anything we want now, right?
Sure.
So, well, soon. So that's going to unlock the past in a way we might not want.
Okay, we'll get to unlocking stuff very shortly. But let's start with the 80,000 programmers that I didn't know were out there who've been doing all this work. What have they been doing on the cloud? What have you seen? I mean, how many of them are trying to unlock stuff using break encryption, and how many of them are trying to sort of get into financial services and sort of change Jpmorgan's results by 0.1? Or how many have actually been doing
That's probably
really
the job
legitimate?
they all want. But so
okay.
Look, so we put this out about 2 years ago, roughly, on the cloud, and we had a small 5-qubit. About a year ago, we upped it to 16, and then a few months ago, we upped it to 20 qubits. So I had laid a bet with my team that when we put it out there, I thought maybe a few hundred people and maybe a few thousand things in aggregate they'll do over this 2-year period. Because I said, wait. I mean, what's going through my head at least was, you need to understand quantum mechanics, you need to understand advanced mathematics, you need to understand computer science. How many people have the will to say, okay, I got all that, and I've got a few weeks to go try this out? So I said, that's the limit. So the actual numbers astounded me. As opposed to the few thousand, that's 4 million. 4 million people have tried different, let's call it programs, experiments, across 80,000 distinct people. So that tells me there's a lot of pent-up demand. Back to perhaps where Martin started off, where people are seeing that the end, or rather classical computers can't solve all the problems they're interested in. So this offers an approach. And that, I think, is what drove them.
And what have they been doing? I mean, what of those experiments? I mean, are there sort of specific areas that you can say there seems to be a lot of interest in this or in this?
So there is a level of intrusiveness we won't do because people are running their own things.
Okay.
But there's a level which we are aware of. Half the people, I'd say, are trying to figure out, is it a real quantum computer? So they kind of are doing stuff at the lowest level. The other half, there are these names you're going to hear soon. There's something called Shor's algorithm and Grover's algorithm, as well as people are solving different Hamiltonians, and you don't need to go worry about it. For those who know linear algebra, think of it as they're doing those kind of problems on it, clearly with the mind of, as these get bigger, then I can apply to solve real-life problems.
Got it. And Shor's and Grover's, they're algorithms specifically designed to show that a quantum computer can do something that a classical one would struggle to do.
Speed up that, I think Cam used the word parallelism is, I think, the best word. So they offer parallelism that is incredible, is the way that those work, but you cannot achieve that parallelism on a normal computer. You need a quantum computer to go do that.
Got it.
I do think these sandboxes have an incredible value for education, actually. If you think of the suite of educational tools that you see in middle school, high school, college science labs, those have a profound impact on how students think about the world. And I think with the quantum computing sandboxes becoming available, if you know a high school student who's super interested in quantum mechanics, you can explain to them what the EPR paradox is, right? You can tell them how these states can be both this and that at the same time, and that there are correlation functions that can tell you that it really is this and that, or that and this at the same time. It's not that this cat is dead and that cat is alive, and you don't know it. This cat is really simultaneously dead and alive, and that cat is really simultaneously alive and dead, and they really are correlated with each other. And somewhere out there in the cloud, there's a quantum system where a high school kid can now go and program that problem, right? And so I don't know how many of your 80,000 are in that category, but for me, as an educator, it's a really exciting development about cloud quantum computing.
Got it. I mean, a lot of people talk about finance as being a promising area for this. I mean, we already had sort of high-performance traders, using supercomputers and sort of pushing the boundaries to try and get that kind of millisecond advantage. I mean, where do you see the potential for quantum computing in finance, and how is Jpmorgan experimenting with the technology?
Yeah, sure. So I think when I look at what we do, now interestingly, like the fast boys style, is a very different type of problem.
Oh, okay. We'll leave the fast boys over
anything to do with that. But
let's take the slow ones.
But yeah, and that's where it is. So in very complex products. So I think about it in 3 ways. I think the first is what I would describe as valuation. So structuring complex financial instruments for specific client needs is very much limited by our ability to compute different scenarios and how many variables you can really put into a model, and what you can do with that model. And so there are lots of things that frankly corporations want and need to manage their own finances, that people, as financial services industry, we don't have enough power, we don't have the ability to do that for them today. And so that is very interesting.
Okay.
The somewhat less interesting, in terms of innovation, but very interesting in the industry is just simple pricing. If I can price something better, because I can run more scenarios, because I know more about it, then you pay less, right? And that's just good, that's just generally good for people, right? I think that the second way that I think about it is really risk management. And this, I made the regulation comment before. It is an increasingly regulated industry, and whether we're, and there are a lot of what I would call constraints, whether it's value at risk is a typical measure that we use to figure out potential loss for something. Increasingly, our regulators want us to be looking at capital, at RWA, at all kinds of different factors that go into, if I'm holding a portfolio, what are my potential risks? All of that comes down to scenarios and running scenarios again and again with different variables and different changes. Again, very interesting. Our ability to manage risk better fundamentally with that kind of advancement in compute for probabilistic computing is very exciting for the industry. I think we would all sign up for safer financial services, and I think that's part of what could happen there. And then the last one, and this isn't unique to our industry, but is true for many industries, is really the data and analytics side of the world, into AI, into ML, and the potential that could exist there with regards to combining those algorithms with quantum machines and what you could really accomplish.
So have you guys bought quantum computers? Are you experimenting with different sets of quantum computers?
No, we're experimenting with them. I don't know how many of the 80,000 people work for us that are, have to go look that up now. I don't think Arvind will tell me. But we do belong to a network, actually, with IBM that does give us access to larger machines that aren't available through the cloud and are increasingly experimenting with them. I want to be careful. I very much view this next few years as a learning exercise. How do you take real world problems? How do you map them onto a quantum space while, in advance of getting the noise reduction down and the coherence long enough and to do things that are truly interesting? But you don't want to start when you've got that problem solved. You want to start now because we do need to train generations of people on how to think differently, how to solve problems differently. And so we're very much looking at that. The room gasped when I said there were, less than 10 people working on it. But when you think about it as a 10-year problem, for a financial services company to be dedicating 10 people who are all very much smarter than I am. And that's the other thing also. We'll come back to workforce, but who are these people? Right? Who's going to change this industry? What are the skills those people need? What are the background experiences? I think that's changing as well, so we should talk more about that.
Got it. Well, one of the people we're counting on to train and develop them is sitting right next to you.
Exactly.
But she also is a specialist in the field of materials, and so can you talk to us about where you see quantum being applied? Because a lot of people say this is the first place where quantum can really make an impact in helping us sort of develop new molecules and understand how the physical world works in ways that simply existing computers can't do.
Right, and so if you look at the broadly defined field of materials and molecules by design, you might think, well, we know the basic laws of physics. Why can't we use that to design materials, to design molecules, to theoretically search the space of different materials and molecules, find out what functionalities they have, and then use that to discover whether there are room temperature superconductors, whether there are giant thermoelectric materials, whether the reactions in certain molecules happen in such a way that could guide drug design, whether we couldn't make better catalysts, for example. So all of those things are problems that materials scientists are very interested in. And there's a loop of people who make measurements, which are people like me, people who grow materials and make new devices, and people who do analytical theoretical work and increasingly simulations of materials and molecules. And we're all trying to get to the point where we have predictive theories. You put these atoms together in this way, and I'm going to give you a room temperature superconductor. Or I'm going to give you a drug that is going to stop cold viruses from sticking on your throat. whatever your favorite problem is. And so the problem with these simulations is that the materials and the molecules are quantum mechanical. So they are really hard to simulate with the classical computer. And actually, if you go back 50 years or so, when Feynman gave a very informative lecture, a very defining lecture about a quantum computer, he defined it as something that could be used to simulate a quantum system in a way that a classical computer cannot. So in many cases, we just need less qubits, fewer qubits for solving this kind of problem than you need for some of the applications that are farther down the roadmap. And so I do think that my colleagues in modeling will be early adopters of this technology.
I mean, how far along are we in terms of being able to sort of model a molecule? I've seen kind of like, I think it's like 3 sort of stages forward. I mean, what kind of advances are we seeing?
Well, there's a lot of effort already, not a lot, not nearly enough, but there's some effort already in trying to model molecular reactions in a way that incorporates quantum mechanics better than it's been done before.
Okay.
But none of that work that's being done with classical computers, I think, is going to be able to achieve what we could achieve with a quantum computer. Actually, for anyone who wants more detail on this, the Department of Energy Office of Basic Energy Sciences just had a really excellent report that came out in October that kind of laid out the roadmap of which materials and which molecules should be the first ones to be simulated.
I mean, I can offer you an example from work that some of our folks did in collaboration with, I'll say, the largest set of CAMS peers in academia. They looked at, like, what's the shape of a molecule, right? I mean, and when we think about whether it's electric batteries or we think about simple molecules like beryllium hydride, which is not such a random example, it is a fairly hard problem to figure out things like bond lengths and angles, because that tells you the shape and so forth. And those could be done on a classical computer, don't get me wrong, but it takes a lot of time and energy. And those kind of fit naturally to what you can do on a quantum computer. So that's already happened. I think the task now is, how do we make this into such a way as these machines get bigger that much tougher problems, which you can't actually do elsewhere, can now be done. And I think that task, I agree 100% with Cam. I think that this is the one that over the next few years will get the most traction, because in some sense, a quantum mechanical system is most amenable to a quantum computer, which doesn't sound that funny when you put it together.
It doesn't, but nevertheless, I'm sure it's important. I mean, we talked a bit about AI earlier on. We kind of brought it up in the conversation. I mean, I was at an event that we held a couple of months ago here in San Francisco, where a researcher got up and showed results from a very basic kind of artificial intelligence challenge. And they used a quantum computer, and it looked like if you increased entanglement, so the level of entanglement, number of qubits that are entangled, you could actually improve the efficiency with the outcome of that compute. Is that really a breakthrough? I mean, are we going to see AI on steroids as a result of that sounds scary. Are we going to see more beneficial AI as a result of quantum computing? Where are we in this field?
So first, it's early days on AI. But I think that what that result showed, because many people thought, I'll be honest, including myself, that AI problems will need much, much bigger quantum computers, and it'll need algorithms which we are yet to discover. And that result showed that you can take pattern matching, which in the end is at the heart of many neural network, deep learning, machine learning algorithms. It really is at the heart of that. It showed that you can begin to break those down into problems that can be solved on today's quantum computers. And the impact of the result is that entanglement was the essential capability needed to get the speed up and the errors down. So then you put all that together and you say, wait a moment, that means as these quantum computers get better, they're going to be able to do problems in AI that today take a fair amount of competition and a fair amount of expense. Now, and that's the first step along that journey. So it is super, super exciting, because I think it actually opens up a new avenue to go study for that which was not known before.
Interesting.
Just to build on that, I wanted to add, if you don't mind. I think for me, what was exciting, I saw the same results actually that you did, I think is the value of the experimentation with the noisy systems, the value of, in addition to the theoretical work and the importance of that, is that can also be informed by what you discover as you are working with the machines that we do have available to us today. And that's a great example of where we learn something through that.
Got it. Cam?
Yeah, I haven't actually seen the paper, so I don't know. But the question of whether those results that you're talking about could have been achieved on a quantum simulator today, right? And so there's the question of at what point do these machines get so good that we have to be doing these algorithms on those machines, right? Is it 6 months from now? Is it 3 years from now? And I do think the jury's still out on that a little bit. Yeah.
I agree.
Yeah.
Yeah, I agree. 6 months or 3 years is not that long when you have to think of a completely new way to do things.
Right.
I do agree there's a window, and we don't know what the window is.
Okay. And finally, another area that I've seen talked about quite a bit is sort of supply chain optimization in general, kind of optimizing various processes using a quantum computer, kind of like the traveling salesman. You know, how do you get him to go optimally around all the destinations he has to go to? Is that something that we could see within a year, a couple of years, being feasible and useful from quantum computing? Everyone's looking at you, Arvin, so I assume that you're the one. I'm looking at you too, but don't worry.
I don't think so, right? And the reason why I'm saying I don't think so is because there can always be somebody really clever who comes up with a way to recast the problem. But at least from what we know today, I think that problem requires bigger quantum computers, so that's why I said not in the next year or two. It's going to be further out. Because a lot of those problems have had a lot of work done on them to make them fit onto classical computers. And so when you look at those problems, up to a certain size, they're going to be pretty good on classical computers. Beyond a certain size, classical can't solve them, but those are too big to fit onto a quantum computer of today. And when Martin mentioned these problems, why do people care? Well, if you're the Royal Post Office and you spend £1 billion a year on gas here, I guess petrol
Thank you.
in the
I'm glad you.
in the UK.
Culturally appropriate comment there.
Right? And so a 10% savings may lead to, actually in that case, maybe £1 billion or close to that. Then people actually care. It's real money.
Wow. We've solved Brexit. Excellent.
So those kinds of problems is why people care about optimization problems.
Yeah,
This is a very simple example. But I think I think
the US president might care about the mail here too. He'd be quite happy with that.
Probably.
Or Amazon. Anyway, yes. But so you think it's because of the lack of compute power? It's just this is going to require thousands of qubits.
It's the combination.
It's a combination.
You require compute power, and my friend there had asked the question about is it software or hardware. You also require new algorithms to be discovered.
Got it. Let's come to the burning question that I always get asked about. What does this mean for encryption? Are we all doomed? You know, doomsday computers, and it's the end of every kind of fundamental, safeguard that we've had up to now. And clearly, there are risks here, and it's no sort of coincidence that I think when I see kind of like all of the spend on quantum computing, there are certain three-letter agencies that spend a large amount in this kind of field. I mean, how much of an issue? Oh, sorry, shouldn't say that. If anybody has got any, I was thinking of MI6, of course, not. Anyway, so seriously, I mean, how should we be thinking about this? Should we actually be slowing down progress here because of the risks until we can catch up and make sure that we've got safeguards in place to deal with this issue, or do we already have them? Who wants to take that easy question?
Well, I'm not an expert on security, cybersecurity, and I don't think any of us on the stage are actually. But
that's okay. Let's have a good guess.
Okay.
And say, which is probably what most experts on cybersecurity are doing as well.
There are quite a few people who are working on ways to make communications and data storage robust against the power of a quantum computer. And so I think there will probably be some kind of an arms race in those technologies. I do think that the point that was made earlier by someone in the audience about how existing data might not be safe is something that's a little bit scary. So someone can steal your data now, which is fully encrypted now, according to everything that can be done to it. And 5, 10 years, that data might not be private anymore. So I do think it's scary.
So the reason that quantum computers are going to break today's encryption is because of factoring of numbers. So just a little bit of the science.
Sure.
So factoring of prime numbers, factoring of numbers which are 2 primes multiplied is a very hard problem. And nobody has figured out how classical computers can do it easily. It can be done, just it's very hard and takes a long time. So that's the basis of all encryption, to make it sort of simple. Quantum computers, one thing which was discovered a long time ago, actually I think in the 80s, is that they can factor these numbers. All right, so that's the basis. If you have a big enough machine, they'll break all the encryption instantly. So anything that is encrypted today, when these machines are big enough, they'll break. And so you can ask, when will they be big enough? And that's probably more than 5 years out. It's not in the first. It's not in the first 5 years.
I'm going to keep a tag of all these predictions, Arvind, right? And we're going to come back to you 5 years' time.
So I said more than 5 for this one.
More than 5 for this one, okay.
But there are known techniques. So the European Union is working on a set of techniques. I think NIST just in the US, National Institute of Standards and Technology, has put out a post-quantum call.
Yeah.
And there is a known encryption technique which is believed, proven may be too strong a word, but is believed by experts to be quantum proof, called lattice field encryption. And the good news is it's as efficient as today's encryption, so it doesn't actually cost you more. And so that is going through its standards process. But I would posit that if somebody is saying, I want something protected for at least 10 years, they should probably seriously consider whether they should start moving to alternate encryption techniques now, assuming that that is important to them to keep it protected for that long.
Bob, you're nodding as a Jpmorgan.
Well,
I mean, you have a lot of stuff.
I think there's 2 things, clearly. I really agree with everything that was just said. I think people talk about the encryption of now and a quantum computer that may exist 10 years from now, which implies that encryption isn't moving, which isn't true. Right? And so I think to me, there is an arms race. It is happening. And I don't think that slowing down, research into quantum computing is the answer.
Right.
I think moving forward aggressively on encryption algorithms is the answer. And I think that's what's happening. I think the historical problem is an interesting one, and I don't have a good answer for that.
Got it. I'd like to sort of segue from there, because one of the big issues we have with cybersecurity is sort of lack of skilled people who can do the work. I mean, some people say there's like a 3 million people shortage. I mean, we think about the cybersecurity workforce. What about the quantum workforce? And that includes people who would work on quantum cryptography. How short are we in the field? I mean, are we at a point where we should be thinking of a very big kind of push into quantum education? And what kind of forms would that take, and who should be responsible for it, apart from Stanford University, obviously?
I do think we should be thinking about it. I don't know that we need a huge push quite yet. I mean, definitely there's no lack of jobs for people who are programmers who can jump easily into quantum. And there's also no lack of jobs at the moment for low-temperature physicists. In fact, the market for low-temperature physicists is surprisingly hot right now.
Oh, that's the quote of the evening. That's the quote of the evening. There's a story there.
Yeah. But I do think that it increases the extent to which generally educated scientists, engineers, programmers, data scientists should know at least a little bit about it. So I do think it becomes part of a general education curriculum in those spaces in a way that it hasn't before. And so in terms of what the demand is for, how many quantum analysts Jpmorgan is going to hire, or how many people it takes.
We'll hire them all. However many you can produce, we'll hire them all. I'll make it that simple a statement.
Yeah.
But more seriously, I mean, like, a couple of decades ago, nobody taught classes on quantum information and so forth. You're now teaching classes on that topic, right?
We do, yeah.
And as far as I recall, I mean, a lot of the better schools have begun teaching classes on quantum information, quantum computing, et cetera.
Right.
I think that says a lot because those are driven partly by research interest, but they're also driven by student interest. So I think that that's happening, and not just at the graduate level, by the way, even at the undergraduate level. So to me, there is a thing there, and that's not just for the expert who's going to go down that thing, right? I mean, would you agree that a physics student or somebody who does linear algebra can probably do some of this stuff?
Right, I do. I think that linear algebra, it's much more common now for students coming in to know basic linear algebra and know basic programming techniques. I used to teach a class called Numerical Methods for Scientists and Engineers, and in 2004, it was the most amazing class people had ever taken. By 2014, even undergraduates come in having already solved differential equations in high school pretty commonly. If they didn't do it in their high school, they've looked it up on the internet and done it for themselves. And so I think the level of numerical literacy in a certain segment of our educated workforce is really high now, and I think that quantum mechanics, the math behind it is not really all that hard compared to what your quants are probably pretty comfortable with.
But I think the interesting thing that I would say there is that to make a prediction, I think that the science background actually is and the physics background in particular, is increasingly important. And I would even comment that more and more of the quant workforce that we're seeing actually have a physics background. And
interesting.
I think that that trend is a healthy trend and probably likely to continue.
Got it. I'm going to go to questions in a minute, so just start thinking.
They also
about
have
questions.
PhDs in math. I should.
Oh, they have PhDs in math.
The double math physics degree.
I wanted to ask each one of you, if you had 3 pieces briefly of advice for any executives in the room who are thinking about how to experiment with quantum computing, where to go, what would you say? And Arvind, you're not allowed to say use IBM and go to the cloud that we have. You have to give general advice. And you can't say bank with Jpmorgan. Okay, but you can say go with Stanford.
But I can say take
you
Stanford
can.
moves.
Yes, so Cam, why don't you, yes, because you've got good, but why don't you start? 3 pieces of advice, what would they be?
Well, I actually, I think it's very application specific, to be honest. So I actually think that reading your articles is a pretty good place to start.
Now
the
that's
checks,
the quote of the
checks
night.
in the post, the checks in the, oh, it's quantum, so it won't be there for another 5 years. Sorry about that.
No, I do think it's very application specific, so I'd have to give that advice.
Okay.
Yeah.
Anything else? Send people to Stanford, obviously. And then 3 would be?
Well, I guess I would say simply don't be afraid. Don't feel like you need to go back to school and get your PhD in physics to figure out what's going on here. There's this big story out there that quantum mechanics is impossible and only very smart people can understand it. And I think you should just set that aside and, and just dive right in. That would be my advice.
Arvind, first piece of advice, don't listen to Cam. But no, you said it's true.
I think the first piece of advice is probably going to be very similar. I would say find, because you said aim it at people who are executives, so that means you probably have some people in your team. Find the 1 or 2 people who are actually curious and ask them to go study the topic, because they'll figure out the application and they'll also come back with this thing. The second piece of advice is this 3 to 5 years looks a long time away. Given it's so different, it's a lot closer than you realize. So I would urge, begin experimenting right away, somewhere, somehow, even if it's going to take a class at Stanford, right? So go experiment, I think, right away is my second piece of advice. Don't wait for a long amount of time. And the third thing is, think about who's going to disrupt you, because somebody out there will go faster and will begin to exploit it. And if they're going to disrupt you, that probably gives you a good idea of how you ought to approach the problem yourself.
Got it.
Right.
Bob?
I guess in addition, sort of building, those are my 2. I only had 2. One is experiment now, try, right? Just go out there and try it. There's plenty of places that you can do that now.
And try different approaches? Or try one kind of thing, fix on one and do that?
I think of it from more like think about the practical problems you have.
Right.
And there are more than one place you can go and try and practice those and work through with either real machines or, frankly, the simulators that exist that are out there. And the second thing is, because it is very academic in nature right now, people are really interested in telling you what they're doing, and so pay attention to what everyone else is doing, and not, so learn through experimentation, but also learn by paying attention.
Right. Perfect. Great. We have time for some questions before I wrap. So, gentleman here, if you just say who you are.
My name is Peter Meyer, and my focus is on creating and dominating new markets. That's what I write about. So this is about applications for new markets. How do we make quantum computing available to creating solutions to problems that people are willing to pay to solve?
The money question. Show me the money now. Who's willing to pay money now to solve, and how can we make people more willing to pay money now?
I don't think we're there yet, to be honest.
Today, I'm not so sure. If we can, I use my simple example, caffeine. Caffeine is a molecule, if I remember, with 160 electrons or thereabouts.
Yeah.
We know what it does. We don't know why it does what it does. So the same thing can be applied to a whole range of things that everyone ingests. If we can solve those, as opposed to in a 6-month wet lab, in a 5-minute experiment on a computer, then there is money to be made because you're speeding up a whole industry, be it materials, which Cam spoke of, or pharma, or food, and so on. Will people pay money for that? Sure they will. So the access to that, be it the software or be it the hardware or some combination, is what people will pay money for. Fertilizer today takes up, I believe, 3% of the world's total energy to produce fertilizer. Bacteria in the soil fix nitrogen all the time. We don't know how. If we can solve problems like that, I believe there's a lot of money to be made. Because remember, fertilizer uses oil, which today is at $70 a barrel or thereabouts. So if you now say that's 3%, you got hundreds of billions of dollars worth to be saved if you can just crack nitrogen from the air and fix it for fertilizer. So these are just two examples of where there is money to be made.
Quantum coffee machines are around the corner. I can't wait. Thank you. Next question.
Yeah, so. Hi, Matthias Untersmeier from Mercedes-Benz. My question is, I assume that general-purpose quantum computers are much harder to build than just quantum optimization machines, and probably the industry sometimes just wants to optimize a certain problem with 2 or 3 parameters to tweak. So first, I would like to know, is this assumption true? And second, where do the industry and the manufacturers meet? What's the need there?
Okay, thanks.
The assumption is not true, because since we can't predict exactly what problems will be solved, we have to build a general purpose machine. Now, general purpose, you can put some caveats around it. I mean, like, you can't do everything possible, but they have got to be closer to what you're calling a universal quantum computer than absolutely an optimization machine, which is only 1 or 2 problems. And so that's what many of us are building, not just IBM. Many of us are building general purpose machines. And so that's the answer, I think, to the question you're asking.
Another way to say it is that, if I may, is that if you are going to solve one optimization problem, and it's an optimization problem at scale, not like 3 paths that you could choose from, any optimization problem that you will solve, you will need a lot of qubits, and you will need them to have long coherence times and be not too noisy. And if you can do that for one problem, you can probably do it for most problems, all problems. It's hard for me to see how you would get to a point where you could build something that can attack a problem at scale better than a classical computer and an optimization algorithm without building essentially a universal quantum computer.
A slightly cheeky question. As you're from Mercedes-Benz, no, I'm not going to ask for a car. What's your interest? What's the company looking at in quantum? Are you allowed to say? Quantum cars. I was going to say, took the words right out of my mouth. Okay, oh, you're interns. That's good. You can tell us everything then, and there's no repercussions. No one's listening. No one's tweeting. It's going to be fine. Ich kann das auf Deutsch sagen auch. Kein Problem. Okay, thank you.
Mercedes-Benz might be looking at turbulence.
Turbulence.
Yeah. I don't know if they are, but some people who do that kind of thing are interested in turbulence.
He's nodding. No, he's not really. He's trying hard. Next question.
Hi, my name is Matt Kinsella from Maverick Ventures. I work in the venture capital industry. First of all, thank you so much. You guys have taken a very difficult topic and brought it down to a level that at least I could understand, which is very, very low level.
I take that as a compliment. I think.
Arvind, and correct me if I'm wrong, but my read was you were quite emphatic that superconductors were the modality that would be successful. And Cam, you mentioned that there was some interesting work being done in some of the laser-based modalities, specifically trapped ions. One that you guys did not touch on is neutral atoms, and I'd be curious to hear what would you need to see from a milestone perspective to come out of neutral atoms to get curious about what was going on there?
Well, I think neutral atoms are quite fascinating. Again, not being specifically a technologist, to me the idea of building a computing device out of anything that involves a vacuum chamber seems difficult. Although people are working on ways to have sort of vacuum chamber on a chip, or trapped atoms on a chip, trapped neutral atoms on a chip, even solid state, even defects in solid state systems like in silicon or in diamond that have some of the same properties that atoms do. So I think that last one for me is what would make me sort of call up my friends who are technologists and tell them, hey, they finally got those NV centers in diamond working as well as the best systems in ultra-high vacuum.
So I think my answer is the reason why I'm on superconducting, we know how to do that using very similar tools or identical tools, processes, and knowledge as classical semiconductors. So since I'm hoping that very soon we'll be manufacturing these at scale, I now know how to do that. On other approaches, we would have to go invent a whole new industry of how to manufacture them. I think what Cam is referring to as the technologists, meaning those of us who build things at scale. And so the other approaches, it takes a long time. You think about the heart of Silicon Valley and back to silicon, it took 10 or 15 years for people to figure out how to take it from a concept in a lab to being manufacturable. And we know how to do that for these.
But thank you for that great question, and I hope your stealth startup in neutral atoms goes well. Next unicorn. Next unicorn. Next question, sorry, I didn't mean next unicorn. One over here. Hello.
Hi, Charlene Lee, I'm analyst and author. Hi, Martin.
Hi.
So my question is, Jpmorgan has 10 people working on this, right? Not very many people. And most companies don't have the scale of an organization like this. So how do we as executives start making the case for putting these experiments in places? Your point that this is only 3 to 5 years away, and it could be the source of huge disruption if you can master this. So how do we get our executives, what's the case that you made at Jpmorgan, for example, to get 10 people? We'll probably maybe get 1/10 of a person if we're lucky.
Yeah, I think that's a great question, actually. For us, well, all right, so we'll start with the fear aspect. I think the Shor's algorithm is a great motivator for many people in many industries and gets people's attention, even if in reality that's the 10-year plus, I would argue, problem. I think for anyone who fancies themselves an innovator in their field, some amount of your energy needs to be going into what I think of. You have your this quarter problems, you have your 3-5 year problems, and you have your 10+ like game-changing problems. And I think increasingly people are realizing some of our energy has to be out here. Now how do you convince your C-suite of that? I don't know them. It's a good question. But I think for anyone who really wants to be seen, who wants to be on that kind of innovative edge of their industry needs to be doing that. And obviously this is one small example of a way that you can do that. But fear might work better.
Okay, another question? Yeah.
Hi, Michael Stewart. I'm with Applied Ventures. We're the VC fund of applied materials. So my question is really on the business model and money side of this. Given that you can do some of the same compute problems that you're showing here on GPUs or CPUs in the cloud, and I can currently provision any of those types of compute and pay for it by the teraflop or pay for it by any work unit, are you already thinking of where that intersects with quantum? Because you have a fairly high capital cost. It has to have a certain amount of compute. Where does it make an X? Where does it cross?
Great question.
60 practical qubits.
60 practical. What's a practical qubit? That's a new one. Is that the same as a logical one?
No, logical is a perfect qubit. So
Okay,
practical
perfect.
meaning that if the error rates are low enough that you can actually go use them.
Got it.
They don't have to be perfect. Just to put a number out there.
And that's 5 years, or?
I said 1 day to 5 years.
Wow.
I gave you that
Okay.
interval.
Interesting.
But for somebody in that industry, I mean, their clients build stuff that takes 5 years to start making money.
Congratulations. One more. Please.
Can you hear me?
Yeah.
So you talked about Moore's Law, and I had a question about how exactly would Moore's Law happen for quantum computing? Is there any feedback loop where the power of a quantum computer will increase the rate at which we can produce them?
A Moore's Law.
I tend to doubt it. I could be wrong, but I tend to think that the sources of error in the current front runners for quantum computers are probably not sources of error that are amenable to being really studied by quantum simulation. That there's just a lot of hard materials work and device design work that needs to be done in the way that semiconductor companies know how to do, except on superconducting qubits. It's possible, though, it's possible that in this materials and molecules simulation area that we talked about earlier, it's possible that there could be a huge speed up of the discovery of all kinds of interesting stuff. And definitely some of the candidates for materials discovery are things that could disrupt the current model of quantum computing.
Got it. I'll take one last question.
Yeah, this is also from Mercedes-Benz, Daniel.
Then you have to give us all a car.
Wow.
No, my question is, what do you think, what's the impact on energy consumption? I know the computers itself, they will be more powerful than whatever we have right now, but it also takes a lot of energy to cool everything down.
Yeah.
So what do you think? Do you think we will save energy by using them, or do you think it will take more energy, or what's your
I'll
guess?
give you our current numbers. I mean, these things take a few kilowatts to run, and that's just for the cooling. They take almost no energy for the actual operations because they're functioning at those ultra-low temperatures. So these are not very energy-hungry machines. I mean, to give you a number, today's supercomputers take on the order of a random number, so 5.6 megawatts happens to be one of the supercomputers I'm quite aware of. Here you're talking like 5 to 10 kilowatts. So these are 1,000 times less.
So it means potentially we can save a lot of energy by using quantum computers.
For the problems they solve.
For certain problems within 5 years, or maybe
And
longer.
if you need to open the case, you have to wait a couple days for it to warm up.
What it does, get cool again, yes.
Yeah.
All right. Now we are going to wrap up, and I'd like some audience participation in my wrap up. As we're at MIT, we like to do an A to Z at the end to just go back over everything that we've covered, but you need to contribute. So I'm going to start with A, Arvin. Please, ladies and gentlemen, thank you, Arvin, for doing a wonderful job. B, Bob. Jpmorgan, do your banking there. C, actually, Cam states with a K, but because I'm a journalist, I can't spell anyway. We'll do C, Cam, thank you. C is also for coherence. We've tried to be coherent this evening. It's also coherence is the length of time in which you can usefully do a compute on one of these incredible machines. C is also for Churchill Club. Please thank Karen and her team for doing a wonderful job. D, I've got disentangle. Anybody else want to come from a D? Because then we're going to go to any Ds? No? Okay. So E, entanglement. If you don't know what that is, you're not alone. But nevertheless, we have tried to give you some insight into that. It's where qubits, distant qubits influence each other, but we have no idea how. But it's really important. Anything else? Cam does. Sorry, Cam does. That's the next session. That's the next session. You have to get a Stanford PhD for that. F is for finance, and make sure that you get that 0.1 right, and don't trust IBM Finance when it comes out if it's on a quantum computer. G is for generally useful quantum computers, maybe within 5 years, maybe not. H, high-performance computing. And we did talk about supercomputers and what's coming, exascale computers. I mean, the other side's moving too. This is a great race, and it's going to be fascinating to see where it goes. I, ion trap computers. Cam can explain what that is if you need further follow-up afterwards. J, I can't think of a J. Can someone give me a J? Josephson's. Oh, unbelievable. You're one of the experts. You know what's going on. Would you care to explain what a Josephson junction is in 10 seconds or less? Not 5 years. No, don't worry. It's very important. Look it up. K kelvins, there are a lot of them there, and it's really, really cold to make this work. L is for lasers, which you fire in ion trap computers, quantum computers. M for materials. This is going to be a really interesting area. We hold a number of places where Cam talked about looking for the opportunity there. And molecules. We're going to finally work out why caffeine does to us what it does once Arvind's finished in 5 years. N, noise. It's a real problem. These computers are very challenging to manage, something that the classical computers don't have an issue or have a very minimal issue with. We're going to need to deal with that. O, I couldn't think of an O. Give me an O. Operate. Yeah, that'll do. But something else. Come on, something else. Others? Okay, that'll do. P. I couldn't do a P either. I'm useless. I don't know what I'm doing up here. Power. Power. Why Arvind's going to make sure that we save the world through reducing power use of quantum computers. Q, obviously, for qubits and quantum leap. R, the time to experiment is right now. Go for it. Do it. Well, that was pretty good. S, superposition. Dead cats, live cats, ASPCA, and they are great. And if you need to understand what those are, it's really important. The ability to be a 0 and 1 at the same time is the fundamental here. T, topological computers, I'll let you look that one up. But T also for temperatures, that's rising in the room here. You've been great, but there's been a lot of heat, so we're going to let some heat out very shortly. U, universal quantum computers, that's the goal. That's where we're going. We want quantum computers that can be used for a broad range of applications, and we're heading in that direction. V, valuation. Bob mentioned a really key use for finance is going to be valuation. W, workforce, the quantum workforce, and how we're going to develop that and how we're going to accelerate America's quantum workforce versus other countries that are moving. X marks the spot where Y, you were thinking what I was going to say for X. And the great news is there's Z, 0 time left. So, ladies and gentlemen, please would you thank my panel.
Thank you so very much for leading this educational, interesting, entertaining conversation. Look forward to the conversation that we might have, say, 3, 4, 5 years from now. So maybe that's when we should, 5 years, we should do it again. As a small token of our appreciation for you, we have the Churchill Club speaker T-shirt.
Yes!
Please wear that in very good health.
Thank you.
Our next program is next Tuesday, the 20th annual Top 10 Tech Trends event. Please visit our website for more details. You have been a wonderful audience.
Yes.
Thank you so much. Good
Thank
night.
you.